All right, so this morning we talked about how much potential AI has, and we covered the state of the art, and we're so lucky to hear about all that. But something else that is more perhaps relevant to us right now is limitations of AI, especially when we're using it in real life. So that's kind of the things that we're going to be thinking about today. So AI is going to just only become more important in this terms of the societal impact. And we're really privileged to be in the position to be kind of safeguarding the medical AI aspect, which we're biased, obviously, but I think it's one of the most important fields in terms of the potential for both benefit to people, but also the potential harm. So the first case study that we're going to look at, so yeah, the agenda is to look at the limitations, but also the ethical implications when we use these AI models in the real world. So the first case that we're going to look at is how algorithms can discriminate, even when we don't have an intention to do so. So what this is a gender classifier made by Microsoft, Face++, and IBM, absolute world leaders in terms of this technology. And they're trying to classify essentially photos into either men or women. Now you can see that for lighter skin individuals, it's almost perfect. 93%, 99% for Microsoft, 95% for that, 97% for that. But for subjects with darker shades, it's significantly less. And you can see the error rate in terms of the models. And that is something really important to consider because before this was kind of unearthed, people thought of accuracy as like an overall score, right? It's just if you have a lot of people, maybe 1,000 random people from society, then how well can it classify? But this kind of disparity really emerges when you examine the accuracy score in more detail and ask questions about that. So even worse is in terms of the racial discrimination, is also discrimination by gender. So this is a sensitivity for classifying gender for dark individuals. So even within this group, there is still more disparity to be found. You can see that for males, it's reasonably accurate, but for females with darker skin, it's a lot less than before. It's almost at the point of guessing. 65% is just better than half, which so you get by completely rolling a dice. So one of the important things to consider here is first, this can be a gap between intention and outcome. So even your model intends to do something really well and solve a problem, it's something important to consider. And one of the most important sources this kind of bias can come from is the bias in the training data. Because the algorithm, if it learned mostly from light-skinned individuals, then it will try to improve the overall accuracy by kind of favoring for the majority. It's like the majority rules. So if we have a look at this example, remember the linear regression example we were talking about? Let's say that the ticks are the majority and the crosses are the minority. If you were to use the algorithm that Aaron just talked about in terms of drawing a line that minimizes the vertical distance between the prediction, which is your line, and the real data, where would you draw this line? If you just use draw to guess. Yeah, you might not go right through the text, which would be perfect, but it's probably going to be dragged up slightly to account for the errors of the other dots. So what's happening in real life is a line of best fit that looks something like this, right? Where essentially we're going to be doing very well for the data that the majority of the subjects are from, but very, very poorly for the other part. So essentially, this example kind of illustrates you almost might need two different algorithms for this. So this is an example. This is a classifier where you're splitting people into, so people can be either dots or crosses, and you're trying to draw a line that splits them. So basically, in the future, if you see a data point here, what your algorithm is telling us is that because it's on this side of the red line, we're going to classify as a dot. So that's what the majority might look like. And the minority data, again, it might need a completely different line. So because what our algorithm does, fundamentally, is to optimize for reducing the most overall loss, you can see that, the other parts, the blue people of the minority, it might just be treated as kind of outliers and doesn't really consider their their needs really. So it would just draw the line probably around there still. And you can see that will do a very poor job of classifying the blue subjects. So this has really, really grave real life consequences. This was a case a couple years ago of a man in Michigan where police had surveillance footage and they needed to identify people from a database. And this guy is completely innocent, hasn't done anything, and he was arrested on his own lawn in front of his kids and wife. And it was the first kind of mistake of this sort, but you can see that, 99% might look really good on paper in terms of reading someone else's algorithm, but even the slight consequences, especially from discriminatory data set, can have really big problems. So this turned out to be, I guess, no lasting consequences as far as jail sentences go, but you can imagine the trauma to him and his family will obviously remain. Now, the problem with this is that our data set needs to be really truly representative of the population that we intend to treat. And why this is so important is because if we do deploy anything of this sort in real life, we can't just, for example, accept other people's training from an overseas test data as verification. We really need to ask the questions and make sure that it is also accurate, just as accurate for the Australian population as well. So any other ideas that we can ensure this in a medical context? Yeah. Yeah, sampling techniques, right? This is kind of going a bit beyond this, but there might be groups that might not, trust due to experiences, they might not trust the algorithm in the first place to donate their data, for example. And how can we ensure that this is our algorithms are optimized not just for the majority of people, but for everyone? Anything else? Yeah, exactly. Like there's so many different diseases in different populations. All things that we need to consider to make sure that the training data is inclusive. And this is another example, but more specific for us. So the consequences is that medical AI mistakes are just not as forgivable as even law enforcement mistakes. So anyone want to try a spot diagnosis here, maybe from the younger year levels? You guys probably see it straight away. Any second years or first years want to try? Yeah. 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 So how did you figure that out? Yeah. Yeah, really good. So for us, our pattern recognition is visible pleural lines, absence of long markings over here, increased radiolucency, mediastinal shift of the trachea. But anyone want to guess how the AI might pick up this as a pneumothorax? Any other features that not really important to us, but important to the algorithm? Yeah, there's a chest tube as well, right? Which is exactly right. So because so much of the training label data sets have a chest drain as obviously a treatment, the algorithm has learned that, okay, if they see a chest drain, there's going to be a more likelihood, it's going to nudge the dial towards a pneumothorax, which is completely unreasonable to us. But remember, a basic convolutional neural network always sees is a bunch of pixels. So it's going to pick up, layer by layer, all the different features. So it's going to pick this up. It's going to know the pattern of a chest drain and push it towards the pneumothorax. And it might not learn the really important features that we were discussing, right? So if someone with a collapsed lung walks to the ED, that is probably where we want an algorithm to really quickly look at the chest X-ray before, say, a radiologist has time to look at it. And with a data set like this, again, it might be really good with with data that they collected, but might not be as good in this case. So this was a ROC graph receiver operating characteristics graph that Chloe was talking about earlier. So basically, so how this graph works is that on one axis you have the sensitivity, and on the other axis you have the specificity. So for example, if you make your AI algorithm, how would you make it pick up everything? Is that you just call everything a pneumothorax, right? Like no matter what image you call a pneumothorax, your sensitivity will be full, but your specificity will be 0 in that. So this is 1 minus specificity. Every single person that you call is probably like not everyone's gonna be pneumothorax, right? So if you make your threshold really low, that's how you can get 100% correct. So basically what the area under graph, so what the ROC graph really tries to show is that there's this balance between, how sensitive do you want your algorithm to be? So you can see that overall, in terms of detecting pneumothorax, it's over here. So that's a pretty reasonable. Oh, by the way, if a graph is like a perfect square like this, what that means is that it's 100% specific, right? Because 0 means that 1 minus specificity is 0, and here it means 100% sensitive as well. So that's theoretically the best, which is why the error on the graph is a really powerful metric, because the perfect error on the graph and the curve will just be 1. So when there is a chest drain, algorithm is great. It's doing better than average. But when there's no chest drain, it does significantly worse. So quite a steep contrast. And that's a really big problem because, again, in real life, we're not going to, like, we're not going to have the chest drain. Like, no one's going to walk into ED with a chest drain. So, okay. And that brings to my second point, which is the importance of transparency in these models. If it is just a black box, we will never know that the algorithm was really looking at the chest chip rather than looking at this. So how can we make sure that an AI model is transparent in addition to just being accurate? Yeah, exactly. So understanding of the trained data set of where it comes from, is it representative of the population? Anything else? Because if you look under the hood of AI, it's just a bunch of linear algebra, like literally matrices, 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 a lot of matrices together. So, it can kind of be thought as a black box, right? So how can we make sure that it's not, and we know what the AI is looking at, what's supposed to be? Mm. Mm. Yeah, just important questions to consider, right? Trying to not just accept an accuracy score for what it is. It's also just digging deeper to see if there's any problems that you might see as a doctor that, say, computer science researchers might not. So this is one of the ways we can do this. It's called the saliency of features. So what that means is that you can see that the AI model is looking at what it's supposed to. So what we got here is looking for is a CT brain, and we basically visually display this, that the more dark the pixel, the more important essentially the network is placing. And you can see that this roughly draws, a slice of the human skull, which checks out that it is looking at the bone, which is what we want it to be. Anyone want to guess what these stuff are? If we're looking at the bone, why are there things inside the skull as well? Of the brain? Yeah, yeah. Good thought, but is the petrous part of the bone? Is that you can't really see from this slice, but it's a petrous part of the temporal bone. Yeah. Okay. So this is like a funny meme of what machine learning is about. I guess maybe not too relevant, getting less and less relevant, but originally it's just basically you pour data in, and what if your answers are wrong, and you just stir the pile, just playing around with the parameters until you bump the accuracy score up, which is, good to bump up the accuracy score, but not very good in terms of a transparent model that will actually, we can see the inner workings of. So this is another case study about St. George's Medical School admissions. They're also very competitive, so a lot of applicants apply. They interview about only a quarter, so about 3/4 are rejected. And of the remaining, they see they accept about 70% of interviewees. And some professor was thinking, okay, well, we don't know these 2,500 people. We're just looking at their stats, right? We don't really see them. We can just read their personal statement maybe. But is there a way that we can use AI to rule out the human biases? So they wanted to put an algorithm here to select all the applicants to the ones that they want to interview. Before we keep going, what are the problems that like red flags that you just might straight up see? This is in the 1980s, by the way. Yeah. Okay. So what do you think? What biases do you think there will be? Yeah. So gender. Why do you think gender will bias an algorithm? Like human might see gender and have some preconceived biases, but why would an algorithm have that as well? That absolutely hit the nail on the head. So that's exactly on the cover. So they want to that they had good intentions, by the way. They wanted an algorithm to do it more fair, right? Because they think that humans might have biases. So what they've done is that they've used historical examples of applicants to the medical school, and their label was who got the interview. So what are some features that might have been docking points from that? And again, so gender was one of them. So being a woman actually dock you points. Anything else? Yeah, race was a big one as well. Like any non-Caucasians got like tanked. Anything else? Yeah, like literally a postcode as well, like the socioeconomic status. So all these, because they used every information they could gather about the applicants, and because the people who were selecting the algorithm, the people that the data were trained off were biased, that kind of perpetuated the bias that kind of then this lasted for years. So this is the timeline. 1982, Dr. Franklin argued that most of the classifications agree. So again, this is very high accuracy. If you see this alone, 95%, like that's pretty good. And we can save so much time, we might make it less labor intensive and more fair. So they they use the historical data to screen all their applicants. And then eventually people raise some flags. Like, why were applicants being weighted by factors like name and place of birth as well? So overseas place of birth actually docked points as well. And then this was really big at the time where the two lecturers, they kind of went forward to report the findings to the UK Commission for Racial Equality. So it's not just racial equality, it was so much more. So, no, all these were kind of used to determine people, to judge people and rank them. And this lasted years as well before, so between the using the historic data and also before people came forward with what's going on. So in terms of that, the goal was to reduce human bias, but it ended up being perpetuating the biases. And did the initial like Dr. Franklin did he intend to do this? Probably not, right? He probably thought that he trusted the people who were grading the applicants, and he wanted to make sure that their biases weren't in place. And he wasn't even hard coding the algorithm to like dock points specifically, right? He just had some data and let it run. So there was no intention anywhere to make it unfair, but that was the result. So over 60 people were wrongly rejected every single year as a result. And that just kind of shows the important lesson of not only how important transparency of how it works is, but also there might be intention to do harm, but harm still occurs. And this is another example, which is kind of even worse. So basically, in I think California and might have been Florida, they were using an algorithm to predict someone's risk of recidivism, and using that, they decide whether to keep people parole. So this was legitimately used in real courts as evidence. So you can search this up, and it's like even the previous example in New York Times was interesting as well. So for over 2 decades, and I don't think I have to say much to, for you guys to guess what factors might bump up the algorithmic. Yeah, it's like you can imagine, right? So, and this has even, I guess, worse. So one is, you don't get into a medical school, maybe not the end of the world, but this one you're unfairly locking someone up. So one of the questions then is, should sensitive features be protected? These are some sensitive features that might influence an algorithm to influence results. So race, gender, age, religion, disability status, sexual orientation, social economic status, immigration status, nationality, marital, family status. So all these are kind of like protected by law, right? So you obviously not allowed to discriminate people on them. What about our algorithm? Should we be able to have access to these features? Yeah. Yeah. It is how it is. And yeah, anything else? Yeah, that's really good. Anything else? So any other features? So we talk about age, how that might be important medically. Yeah. Medical context. So your infectious disease, mental health. Yeah. So we can probably go through every single of them, and we will be able to find, like, it's just the reality of medicine, right? It's complicated because all of these, they are going to be influencing someone's probability of certain conditions. So basically, it's not that easy as far as medicine is concerned to kind of like hide all the features and call it a day. So what that will kind of be unbiased by blindness, in that they can't be biased because they don't know your sensitive features. But that's a problem as well, because I think a while ago, what Facebook tried to do was that they're not allowed to target ads based on things like sex and stuff. But based on someone's like, Instagram real history, for example, you can really easily predict someone's sex. So can you see how these features and age as well, like depending on what your interests are, we're not going to get it exactly right, but all these can be predicted somehow using features that have nothing to do with you. Like for you, they might not know your age, but if you, I want to give some specific example, but like, they, it's really easy for an algorithm to use other features to kind of make age an output predictor, like something they're trying to predict now. So it's almost impossible to remove bias by simply blinding it. So that will kind of be like literally covering an ear and pretending not to hear the problem, right? So what other ways are there that we can try to, so what you're talking about right now is, rather than using accuracy as a sole feature, what are the some measures that we can do to make sure that our algorithm isn't being biased? Yeah. Mm. Yeah. So really good question. But the problem is, it's just really hard to, like, for example, if you have an algorithm that you try to like say, a certain population is 1% of the real population, but you make the training data set 10%. can you argue that's ethically unjustifiable because it worsens the result for 99% of the people? Yeah. So we're going to have a maybe just talk for 5 minutes about this. And we're going to talk about some other ways that we can measure accuracy that make sure that there's parity between different groups. Okay, does anyone want to share their thoughts on what metrics we might look at to make sure an algorithm is as unbiased as possible? So, yeah, anyone want to share what they talked about? Yeah, go for it. Yeah. Mm, mm.
Do a bunch of different checks based off those. That can also particularly mainly based off
Mm.
about some differentials in like unique investigation.
So are you kind of thinking of only using the sensitive features where it's necessary? Is that kind of the proposal? Yeah. Okay. Anything else? Hmm. Yeah, really good. So that's kind of exactly why we can't just you know, say that because our model doesn't know these sensitive features, therefore it can't be biased. Because there's so many ways to predict the sensitive features. So, and also only using the models when necessary is absolutely great. So for example, there's just some conditions that, age might be really important, but would you ever need to know someone's religion on some models? Like it's hard to argue, right? Hey, it's okay. Don't dig your hole. It's okay. It's okay. Yeah, that's okay. No, honestly, fair enough. Like if you can justify a reason, but see, we can. So the problem is, it's not like we shouldn't include these sensitive features, right? It's just that we need to make sure a model performs just as well for all the different groups of the population. So these are some statistical measures that we can make sure. The first is parity. It's an algorithm satisfies parity if the probability it makes a positive prediction is the same regardless of the condition or regardless of being conditioned on a demographic variable. That's just trying to say you can't have a preconceived notion that you have one group of people, it's just initially way more likely to think you're going to do something or have a condition compared to another demographic. The second one is calibration. What this says is that the probability of your algorithm being correct is the same regardless of demographic. So they still know the sensitive features, for example. They're just as good at what you're predicting, whether you're like men or women, what race you are, or whatever sensitive feature that we want to check for. And the third is the equality of odds. So it satisfies the equality of odds if the probability that it predicts a positive outcome is the same regardless. So the same regardless of demographic, given that the outcome will occur. So this is like almost going the other way, right? So it's not saying that if an outcome does occur, that we are more likely to kind of trace it back to any sensitive features. There's a lot of statistics, which is really interesting about how these stuff works. So if you guys are interested, I've linked the reader page to the probability course, and it's just one page that's pretty accessible. Okay, so let's have a look at this discussion now. This is a hypothetical, not a case study. The first part isn't. The first part is real. Yeah. So liver transplant is the only curative measure, the only curative treatment for end-stage liver disease. And as part of the Liver Foundation's criteria, patients who are unlikely to stick to medical advice and rehabilitation, for example, if they continue to drink alcohol or consider a high risk of returning to heavy drinking after a transplant, are not eligible. So what you've done is that you've designed a deep learning algorithm that takes into account, so in terms of the input, is a patient's entire EMR history. And you provide a probability of transplant success. And based on data, historical data, is more accurate than an interdisciplinary team of healthcare workers. So what essentially your model has able to do is be better at predicting who will have the best life after a transplanted liver. So before we continue, any concerns, any questions, any thoughts anyone wants to raise? Yeah, so in terms of so the outcome they're trying to measure, yeah, it's let's just say it's length of survival. Yeah, absolutely. The EMR holds so much information about someone's life. It's crazy. And if you were to put all of that into the algorithm, and the algorithm has access to all of that, you know, it's very similar. It could lead to similar problems like we talked about before. So what we're going to do now is there's 3 questions we're going to think about. First, should it be allowed to know the patient's sensitive features in terms of all the EMR? Should it, our patients, and so it's statement. So our patients should not know that their transplant priority is determined algorithmically. And the third statement is doctors should not be able to influence the decision made by the algorithm. So we're going to have a debate here. On this side of the room, you guys will be affirmative. And on the other side, you guys will be negative. So can you try to do maybe 3? So I think this is already 3 tables. Do you guys want to be a group and then people in the middle a group and then people at the back in the group? So you guys at the front of the room, you get topic 1. Topic 2 on the next. So our patients should not know the transplant priority. And number 3, doctors should not be able to influence the decision made by an algorithm. So you guys are affirmative and these guys are negative. And after 15 minutes, we'll have 1 speaker from each team to present an argument. Do you guys want to join, sit together with them? You guys are 2. You guys are 3. Minutes until we start. 4 more minutes. We'll start at 3:05. I will algorithmic do a Python random who's going first.
Yeah, I was like, should I add more? I didn't have time last night.
Yeah, I'll do it. Oh my god. Oh.
Love it.
Okay, are we all ready? In the spirit of true fairness, I have imported random, and we'll go rand int 1 to 3. So that determines which pair of is going first. So, okay. We are starting with debate number 2 first. And then number 1. And then topic 3. Okay, so okay. Okay, so I will knock at 3. Knock at basically at 50 seconds. Okay. So I won't just play this, might be a bit pressure. Okay, so whenever you're ready, I'll get the topics back up. Oh,
Discussing use of this. So like the stimulus doesn't really state that we have to just use an algorithm to as a way to create like a transplant list. And so we could instead use an algorithm as a base and then incorporate doctor's notes and then have like a team review the list that the algorithm makes from those notes. And so then there's no real need to disclose that information to the patient unless they ask. Because well, you're incorporating like your doctor's ideas and your doctor's like obviously their opinions on you know, whether or not they should be, you know, what ranking, I guess, on the transplant list therefore. And then the algorithm is also being like heavily reviewed and criticize and then challenge, and therefore, unless the patient really asks why I'm either really low or really high on the list, it's still kind of taking into consideration a large team, and therefore that's why kind of to be disclosed.
Okay. First speaker for the affirmative side, the negative side.
Okay, so this wasn't exactly how we framed the debate, but we're not going to challenge how that is, right? So we're going to say holistic algorithm with a team of doctors or interdisciplinary team. That's great. We accept that. That's fine. In either world, though, an algorithm is still being used to help this patient. So in both worlds, we're getting the same result, the same list of patients, the same people who are going to get those organs. But in one world, they don't know, and in the other world, they do. Whether or not it has the biggest effect, the algorithm, or the smallest effect, in regards to patient comfort, which is the main metric upon which this debate lies, we are improving patient comfort because they have the most knowledge about how they're being treated, how they're being assessed, right? There is no possibility for them to find out they've been lied to and therefore impair their trust in the medical system. So because the result is a wash, the result in regards to the organ transplant is a wash, it really just comes down to knowledge.
Okay. Second speaker.
We do see we did come across the idea that them not knowing that this could actually be so we talked about like the doctor and patient relationship and how it's a incredibly important dynamic in healthcare because obviously it comes with a lot of trust. And the thing with this trust is that patients entrust us with the information about their health and to be able to deal with it this way to provide sound decisions. However, they could see the use of algorithms as a bit of a betrayal rather than the holistic approach that we've been talking about by combining it with doctor notes and resources. So we think that using that they don't feel the idea that maybe, say if you were a patient, you were to find out that the doctor who was treating you, like it wasn't actually their complete decision, they could see it as that your doctor is a bit incapable of treating it, when in fact the only thing that's is minimizing bias that could happen. Can have bias, but obviously a person can have intrinsic bias depending on the decision. So those are just the ideas we discussed, and that's why we feel that in order to
Okay. Thank you for that. Second speaker for the negative side.
So the proposition said that the level of human bias is typically higher than bias that we might see in a well-designed algorithm. So then it stands to reason that patients might feel more comfortable with the fact of knowing that their decision making is in the hands of an algorithm rather than the person who's capable of making mistakes. And the way to think about this debate is that we should think about the cases. So the first case is that transplant priority isn't determined algorithmically. In that case, the patient should have a right to know that it's not determined algorithmically. So that's kind of an obsolete case. But we should also think about two other cases, which is one is that the algorithm is a good algorithm. So it does a good job in determining who should get a liver transplant. And in that case, it stands to reason that we should inform patients that an algorithm is determining their order. And if it's a bad algorithm and it's also being used, it's even worse if we hide this from patients and tell them and we lie to them about an algorithm not being used. So in the case of a bad algorithm being used, it's really important for transparency and for kind of open sourcing the kind of decision-making process so that we can get feedback from patients. And we should definitely not be using an algorithm in secret to determine whether or not a patient should get a liver transplant.
Okay.
Currently at this point,
Okay, so our final speaker for the affirmative side.
So going from 25 So first of all, is the idea that the first speaker on the next two mentioned that not disclosing the information to the patient would be lying to the patient. I think that's a bit of a misconception around what would be happening there. If the patient was to ask, I think it's perfectly valid to explain it to them. It's just coming up front. I don't know if it's necessary to give the patient that information that, hey, your transplant decision is going to be in the hands of an AI. I think that undermines patient trust in both the and in the healthcare practitioner. That leads into kind of a point made by the third speaker as well, is that aren't patients more likely to trust the well-designed algorithm? In which case, I ask you all to consider if your own organ transplant decision, or one of your family members was in the hands of an AI, I think you would all agree you'll be more comfortable with it being in the hands of a human team. I'd also like to challenge the second speaker's point about those three different outcomes. The great point there, but the debate tells us it's a good algorithm, so really only one of them is valid. And even in that case, even with a good algorithm, I think most patients now, almost all patients, would still prefer to have that trust of that team rather than machine. That's the case.
Okay, thank you for that. So the reason this is a debate is because genuinely, right now, patients aren't really privy to the conversations made by the board. So is it any different if a machine does it rather than a board? Things to think about, and both teams raise really good points about, does that undermine or strengthen your trust in the healthcare team? Okay, the next debate will be topic 1. Are we trying to do third speaker? Oh, sorry. Oh, okay. Third speaker for the negative side. Whoa. We can't go twice. Yeah. Disqualified. No. Third speaker. No, it's in like there needs to be a third speaker. You spoke already, didn't you?
Yeah, I know, but no one else was speaking.
Nah.
Ah,
You can't do that. You can't do that. Come on. Someone needs to speak. Come on. No, come on. No, we seriously. Come on, guys. Someone volunteer. You can rebut. You can rebut their team. Okay, no, just okay. I will start your time. I'll start. Okay, fine. Barricade, you have 30 seconds to make the biggest slam dunk rebuttal. Starting now. 30 seconds. 30 seconds.
Okay, so when I have a doctor and they use a deck with them to see that my bones are brittle, do I think the doctor is incapable? Do I think they have some inability to do something? No, it's just the same thing in occurring when we're doing this. And in regards to the opacity of a board, at least in this case, we know that it's something that we can appeal. And we still know because they still get an impaired trust in the medical system. They're going to find out that they didn't know about it, and that is still a lie.
Okay, thank you. Let's all give it up for Barricade Lamar. Okay. So can we pass the mic on to table 1? Can we pass the mic to table 1? Starting.
So, approach the affirmative argument for that the algorithm should be allowed to make patient features, and we use the examples that listed previously on the slide. We had 2 key arguments, which was that allowing it to know patient-sensitive features will allow maximum clinical benefit for the patient, the healthcare system, and society. And it will also allow monitoring of the equity of the performance and whether there's discrimination occurring based on unmodifiable and therefore untrustworthy patient. So firstly, I'll talk through maximizing the clinical benefit. Some patients, their sensitive features should really be taken into account because we don't know the difference in, say, the length of average survival between, say, males and females, which would be considered if it's extremely different and if there's likely to have an extremely different benefit, say if females are likely to live 10 years longer with a transplant, we believe that this should be something that's taken into account so that we have a finite resource of livers. We also raised the point that some items, for example, disability status, could be important where patients might be, say, unlikely to benefit if they have a specific genetic disability or chromosomal disorder, that they actually might benefit. And that was our main first argument, which is we wanted to maximize.
Okay, thank you. First speaker from the negative side.
Okay, so our main argument was that by taking into account sensitive features, you're perpetuating the worst outcomes for the groups that are already doing poorly, and perpetuating good outcomes for groups that are already doing well. So as an example, if a high socioeconomic group had a higher chance of living longer, you're giving more livers to them, which further allows them to live longer. But if we're looking at equity in healthcare, we should divert more resources to those who are doing worse, which is why we allocate more funding to those in a worse socioeconomic area. And the reason why things like closing the gap exist to help reduce the disparities between different racial groups, such as Indigenous people and non-Indigenous people. So by taking into account those sensitive features, you're basically perpetuating the disparities that already exist and further make.
Okay, thanks for that. Second speaker for the affirmative side.
Hello. Thank you for your points. I think whilst it's understandable to believe that implementing a system where we include patient-sensitive features into the algorithm could lead to inequities, as you suggested. However, we believe that this algorithm is part of a much larger program where it does require consistent monitoring of equity and the performance of it. In addition, when we talk about liver transplants, it's quite a significant procedure. A transplant of a liver is quite rare, and giving it to someone simply because because we want to eliminate prejudice or avoid discrimination is in fact doing injustice to the patient who would otherwise be benefiting from the liver in the first place. And finally, we also want to talk about how it's almost impossible to rule out bias in clinical practice. And when we include these sensitive features into an algorithm, we're using as much information as possible to make an informed decision. I believe the future of medicine is getting as much information as possible, so we need more information in our decisions and no less. Thank you.
Thanks for that. Second speaker for the negative side.
Yeah, so the affirmative side makes some interesting points regarding the monitoring of equity. I think the idea of monitoring an algorithm constantly is a good idea, but I think it begs the question of who's doing the monitoring. I think trying to remove bias by adding oversight from inherently biased humans may not lead to the outcomes that we're necessarily trying to produce there. In terms of our second point, the idea is just that fundamentally it's hard to see whether those sensitive features are clinically relevant in terms of the outcome for the patients. Things like age and predictive factors around gender, as my previous speaker said, are just going to be favoring the bias that's already inherent within the literature and within the current system. And things like that should not be given as much weight as other more relevant features such as past medical history, things of that nature.
Thanks for that. And the final speaker for the affirmative side.
Thanks for those points. Few things that we quite like to close with is that at the end of the day, the sensitive factors are the things that influence the likelihood of a successful liver transplant, as defined here as the longest length of survival. I think if you ignore these factors, you go to a place where you give liver transplant just based on what's equitable, and you might have a limited resource that only lasts for a month in a patient, whereas that liver given to a patient whose sensitive data is taken into account, that liver could lead to an increased lifespan of 5 years. And I think when you're looking at limited resources, at the end of the day, there is someone who may not benefit and someone who will benefit, and it's about maximizing the limited resource. And in medicine, sensitive factors are used in all algorithms and they lead to different and improved outcomes. And ignoring it and looking at things blindly, that's not truly reflective of the patients that we treat.
Thanks for that. And now the final speaker for the negative side.
So, what, it may be possible to predict things like the longer lifespan that a patient may have through an approach like this and implementing those sensitive features. One thing that it sort of fails to account for is the quality of life that the patient will experience following the liver transplant. And to sort of predict those factors, you don't necessarily need those sensitive features. And things like, for example, the patient's psychological status can play a much more significant role in how well they sort of live the remainder of their lives. And in terms of the last point that we have to raise, I think hasn't really been touched on, is that the source of this data, as it's listed in the front page, is from the EMR itself. And the EMR is written by the doctors. So there's possibility for bias in the entries that are put into the EMR itself. So that's something that needs to be considered, and it's possible that this sensitive data that we're collecting is inherently biased right from the get-go.
Oh, perfect timing. Okay. Yeah, really interesting debate. I think both sides raised really good points. And something that, especially what you said at the end, is the EMR, is that reflective of a person's life as a whole and their future predictions? Is often the people at almost maybe the lowest point of their lives, right? Sometimes when we see them. So another important point to consider. Okay. Thanks for that. That was amazing. Huh? Fourth speaker. Okay. So last topic. Okay. Feel free to start when you're ready. Thank you for that. First speaker for the negative side.
So the doctor should be able to influence the decision by maintaining patient trust, but also because of the differences between the consideration of humans versus AI gifted human life. So as another debate raised earlier on, would patients wholly trust algorithms with liver transplants, which are a life or death scenario in many cases? There is this fundamental idea that doctors are the guardians of human life. And the reason why we do place such enormous trust in other humans, medical professionals, is that other humans know what it is to be alive. We share the same experience of life with all other humans, and therefore we understand intuitively what the value of life is. On the other hand, an algorithm, as per what we were talking about this morning, just values human life, or like the amount of years that someone's going to live after a liver transplant, as a reward which is just going to reinforce a certain pathway and produce a certain action. So in order to maintain this patient trust, and also to ensure that the value of human life is maintained, we could have a panel of medical professionals just to vet the decision made by the algorithm at the end of the day, and just ensure that we are valuing life as.
Thank you for that. Okay, second speaker now. Thank you.
Yes. It's raised by side. So just my phone. So talking about the idea of using an algorithm to decide if a person is going to be fit for a liver transplant based on whether they're likely to change their behaviors or not. Now, there's a couple of problems with this, but first, I think we all know that life is not like a linear graph. You can't just predict the future or future behavior of somebody's life or their trajectory just based off the first few data points that you might have. So, but an algorithm that just looks at a person's history doesn't take any of this into account, and they sort of just go based on the patient's past and their behavioral patterns. They kind of try to determine how that person is going to behave in the future. I like to think that we're a bit more complex than this, and yeah. And then our second point was that in order to use such an algorithm accurately, you also rely on the quality of inputs. So an algorithm is only as good as the data that we can feed it. But in order to have like good output, we need to have like a comprehensive history of that patient, and that's not always guaranteed, especially for people from lower socioeconomic places.
Thank you for that. Final speaker from the affirmative side.
Yes, I guess. A primary argument is that like this list isn't necessarily going to be deciding who's getting a surgery and who's not. Rather, what the list is doing is just providing who, like, if we had unlimited resources, who would get their liver first. But in this case, yeah, there are other factors that we want to consider in terms of like logistical factors, as in terms of like the accessibility for surgeries. And in this case, we yeah, ultimately we think doctors should not be able to influence decision made by the algorithm to ensure that we don't introduce the doctor's bias into that decision. And hopefully based on that, we can then decide based on those external factors what we think is best. And I guess the other thing with what we're working with the EMR, it is based on the history, but the doctor is also predicting based on that patient what they think the likelihood of injuries can be in terms of whether they can not continue drinking alcohol, etc. And so ultimately the algorithm is supposedly more accurate, but the doctor should have that.
Thanks for that. Final speaker for the negative side.
Okay, I just like to start. Just like guess one of the main like overall concluding problems with this sort of statement. It's a very general blanket statement saying that in any sort of circumstance, a doctor cannot be able to influence the decision made by the algorithm. And that's what we exactly disagree with. So going off of what the affirmative team's first speaker said, yes, we do agree that the algorithm might be more accurate on average, but there are obviously very specific circumstances where there are going to be some determining factors that are a lot more subjective and actually can be a very, very minute little difference that can change the position of the ranking of one transplant recipient compared to another. So it's really incredibly hard for an AI to be able to take into account more of the subjective matters. And that's what our second speaker, Matthew, was saying, that there's a lot more that needs to be also taken into account by the doctor. And you also have other things such as like support systems and social connections and the overall environment that also can change the likelihood of whether a person can relapse into, like, for example, alcohol or tobacco use after like getting their transplant. And also similar, can I just mention? Second speaker also mentions that the doctor should be able to work with the algorithm. I know that it said that the ranking shouldn't be changed, but I still believe that when we're talking about this, there are going to be, again, certain circumstances that have to kind of override this little minute things that perhaps change the ranking a tiny bit. And I'd also like to emphasize the fact that not one doctors should be overriding this sort of system. There should be a panel of doctors. Shouldn't be some sort of like veto power thing, but there should always be some sort of supervision of the algorithm. And again, the quality of inputs must also be taken into account and how well the AI can actually analyze that. So
Thanks for today. Can we have a massive round of applause for all the speakers? Like, just none of the third party debate, none of you guys have debated before, right? That was amazing, especially for your first time. Oh, absolutely awesome. Okay, so yeah, really interesting points, because really the only data that we have to work off is EMR data. And I think everyone really mentioned is how representative of that is that of the really the life that someone lives. Really, is that good enough to really be determining their future? Yeah, interesting things to think about. So again, we don't really have answers for this because this is still something that's work in progress, and it just things that we should all be thinking about going to the future. If you do see these AI models in the wild, hopefully questions that you will think about. So the last thing that we'll talk about, just a quick thing on privacy. It's a huge topic that honestly deserves its own workshop at this point. But just some really important points is that privacy matters at every single step of the data collection process. So in the training, where are some points in which we need to protect the patient's privacy? Yeah. Yeah, like where can there be a privacy problem, really? Yeah, it is. Yeah, indeed. Yeah. Yeah. So things to think about is like, what's the thing about autonomy? Like, how much should patient know? Like, if their data, if they consent for maybe one like the research, does that mean that going into the future, their data will always be accessible by all the algorithms? So basically what I'm trying to put here is all the points that we really need to be careful of. So the reality is there needs to be lots of patient data, and there's just going to be sensitive features because that's how medicine works. And only with these sensitive features, we can't just get rid of them, because if we get rid of them, then how can we ever check that the algorithm is not biased, right? So obviously this needs to be stored somewhere, and it needs to be stored somewhere as well, because all the data needs to be somewhere initially collected. It needs to be transported probably to the computer in which a training takes place. And even then, when it's transferred to team collaborators, like who has access to these data? How easy is it to access it? And if you're not training your own computers, what measures are, for example, if you outsource your computing power to Microsoft and Google because they've got the biggest machines, then what steps are they taking to protect our patients' data? The second thing is deployment, because it's the important thing about where does the computing take place, right? Is it going to be sent up to a server anywhere, for example? Like all the data that you're going to be putting as input. So after the algorithm has been trained, if you want to answer the question, then where would that take place? How about, like, what are the steps we're taking to minimize the risk of data leak? What are the steps that we're taking to make sure that the data has been completely anonymized? And lastly, again, is patient autonomy in terms of, if you consent your information to be used in research purposes, like how much should we inform people what we're doing to the data? So the last thing is environmental impact. And to be honest, this is something that I was really thinking of before putting together this presentation. Does anyone have any guesses on why AI is actually having a really, really massive environmental impact? Yeah. Yeah, energy use. Like, it takes like $1 billion, right, to train one of these models and to update it every now and then to be up to date with the world knowledge. What else were you saying? Yeah, like computers are like our computers. You might think, oh, we just charge it for a couple hours and we'll be fine. But the data centers that I'll be showing literally has, it's literally the size of a football field and bigger. It's only going to get bigger because the only way to make the large language models better, we're just going to need bigger data centers and more data and more computation time. So this is Bitcoin, and it's kind of outdated at this point. But how insane is that? Australia uses 188 terawatt hours of electricity, and Bitcoin itself uses nearly Australia and more than most countries. like bank, like this, it's just unreal how much power that Bitcoin will use, like how much computing power that devours. So AI is kind of going into that in terms of they have billions of parameters and they run on enormous data centers. So this is the Microsoft one and Iowa, where part of the ChatGPT 4 is trained. And not only is it electricity, but also is the water used for cooling all these data centers. So basically, since OpenAI has really become exploded to the mainstream, the water use has increased by 34% by Microsoft. That's 6.4 billion liters of water. And this is not just a Microsoft problem. Every company that is using AI are going to run to this issue. So just guess, how you guys see that? But how much one conversation with ChatGPT, how much water would that we use? You saw it already, right? Okay. Did you guys see it? How much? Okay. Guess how much water? Milliliters of water. One conversation with ChatGPT we use. Is in milliliters. Yeah. So it's, yeah, it's pretty close, right? So conversation. So this is based on the Iowa. And this is a link to the paper you can read. And just a disclaimer, like the reason this is 5 to 50. Look, but yeah, it's a really good question, because the reason that it's such a big range in terms of how many queries is because if you use like solar power, that doesn't require much water in the electricity generation stage. But if you use coal, then that's huge amounts of water. So this paper was studying the Microsoft data centers in Iowa, and I think those guys are using quite a lot of non-renewable resources. So that was a bottom range, right? So every single time you ask 5 shipping questions, you're using like a whole bottle of water. Like how insane is that? Like it's just things that we don't really think about. Like it seems as if it's so clean and fast, but in the background, huge computing resources were necessary to make this happen. So have a read of the paper. It's really interesting. So this is something that the author said: the global AI demand may be accountable. So this is not, so before it was 6.6 billion liters, by the way. This is cubic meters of water. It's like a meter, like a box of water. Right? Like it's not just a liter, like it's not, yeah, it's like a huge box of water, and 4.6 is like incomprehensible in 2027, and that's half of the UK's water use, like a whole developed country's water use. So absolutely massive. And this is a question that I want to pose. Is there anything we can do? Stop using ChatGPT. Like I was personally responsible for a lot as well. Yeah. Wait, sorry, guys. Guys. Yes. Yeah, go. Guys. Yeah, we can. Mm. Mm. Yeah, we can vote with our wallet and be more conscious. Anything else that we can do? Yeah. 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 So the AI engineers, they just after work, they go to the sauna. No, the water. Oh, yeah, yeah. Yeah. So make sure that honestly, things to think about. Like, is there maybe sauna? Like make a huge sauna center next to ChatGPT. But just in general, is there a way? So that's not something we can do. That's something that engineers can do, right? They can like try to use the water more efficiently, not wasting it completely. Anything else we specifically can do? So no one's gonna use ChatGPT anymore. No, but it's the same thing. Like honestly, like we can look into their company's like statements in terms of what they're trying to do, but I feel like at this stage, maybe all is hard to choose. Google's doing the same thing as Microsoft. It's not just a Microsoft problem. And I'm not sure about Anthropic. Maybe they're good. But it's just, maybe we can do things like prioritize. Yeah. Infinite money glitch. Infinite electricity glitch. Also, just yeah, so for water, it's actually not all the cooling. A lot of it is from cold, like the steam turbine. So if we use clean power, that does reduce like a lot of it, because mainly it's electricity that's a problem. But yeah, honestly, good thoughts to have, and just something that I think we should be aware of, because I don't think many people think about, like, every time you use ChatGPT, just bottles of water just start getting poured out, Okay. So so that's all for the afternoon workshop. And before I hand it back to Claude, can we just have a massive round of applause for how much he's put behind the scene? It's honestly an impossible task to convert 4 weeks of a Stanford University course to be condensed in 4 days. And the number of messages I've woken up to, like, in the morning, where he's been sending, like, doing stuff at 2 a.m., 1 a.m., even last night, is unreal. So can we have a massive round of applause?